Okay, great. Hello and welcome everyone to this special webinar. My name is Ilya Karnaukhov and I'm the Development Manager at World Forum Offshore Wind. And today's webinar is on white paper highlights, mooring systems for floating offshore wind. It's my great pleasure to welcome our whole panel today. So we have our speaker, David Timmington from Griffin-Woodhouse, as well as a great panel of offshore wind experts who all greatly contributed to this white paper development. We have Alistair from Catapult, we have Ralf Skowronnek from Skowronnek and Bechnak, we have Jon Gumley from Moorsure, and Aseem Dhingra from DNV. And I'm very sorry if I pronounce your name with an accent. I tried my best. And before we jump into the presentation, let me tell you a few things about WFO. So the organization was founded in 2018, and we're a nonprofit entity focused on offshore wind energy only. We promote offshore wind energy, and our members represent the complete offshore wind value chain. We have an international setup with offices in Hamburg, Tokyo, Taipei, and New York. And in terms of our activities, it's very straightforward as we focus on three things. We provide advisory services for offshore wind around the world. We inform about offshore wind via a number of media channels, and we organize events for connecting the global offshore wind community. And it's also important to briefly mention our floating offshore wind committees that consist of our general committee. They meet on a quarterly basis to discuss initiatives of the committee and introduce new proposals. And 4 subcommittees that meet on a monthly basis and conduct all deliverables, such as the mooring system white paper that we're discussing today. Currently we have moorings, insurance, O&M, and cables and substation subcommittees. Only WFO members can participate in committees' regular sessions. And in terms of our members, we're very happy to have over 85 global members from around the world, which represent all segments of the value chain from North America, Europe, Asia, and Oceania, including Australia. And if somehow you are still not a member of WFO yet, please make sure to contact us. Feel free to reach me or our Managing Director, Gunnar Herzig, and we'll be very happy to answer any questions you have regarding the membership. And a few words about this structure of this webinar. Special webinar, and it's very simple. In the very beginning, David will give a brief introduction to the white paper highlights for 10-15 minutes, and then in the remaining time we'll have an open panel discussion. So it's a great opportunity to all of you, for the attendees, to ask any questions you may have. Each listener can ask a question using the chat function on your control panel on the right hand side. So without any further ado, David, the floor is yours.
Great, thanks very much, Ilya, and also a warm welcome from me to all attendees today. It's been a privilege to chair WFO's Floating Moorings subcommittee. The assembled members represent an unparalleled level of knowledge, experience and expertise across a wide spectrum of industry-related fields, which is evidenced by the composition of our panel today. A collaborative ethos has encouraged wide-ranging discussions around a broad theme of integrity management during regular monthly meetings held since January 2021. The subject matter is diverse, can be complex, and we have covered many topics. This inaugural white paper, therefore, reflects these varied discussions and consequently covers a lot of ground. We've tried to achieve a fine balance between being sufficiently detailed whilst remaining accessible to the lay reader. We trust it clearly introduces the main concepts and design choices with respect to float moorings, identifies key considerations relating to integrity management practices, and points towards future detailed work of the subcommittee. And my personal thanks go out to all who contributed to the white paper. Those of you that have read the white paper will understand it would take at least a full hour allotted to today's seminar to review each section in detail. So today we propose to provide a brief synopsis of the paper, draw out the main points and highlight key messages, leaving plenty of time for Q&A and hopefully stimulate an interest to read the white paper later at your leisure. Our panel today not only represents specific fields of expertise, but also organisations and publications extensively referenced within the paper. So their comments will be particularly relevant regards the novel approach our industry needs to adopt in supporting net zero ambitions. Next slide, please, Ilya. So coming on to the brief summary of the white paper contents. Firstly, we introduced the now familiar substructure design concept derived from offshore oil and gas seen here. Spar, barge, tension leg or TLP, and semi-submersible, the currently favoured choice of many developers. Fundamentally, station keeping or mooring systems should maintain the position and attitude of the floater whilst protecting the dynamic power cable. And foundations can be compliant or restrained with respect to global motions, which are described as the 6 degrees of freedom: surge, sway, heave, roll, pitch, and yaw. Simply, the mooring line transfers loads acting on the floater to anchors installed on the seabed, and mooring configurations vary from plain catenary to multi-catenary, buoyant semi-taut, and taut, as illustrated here. There are so many parameters with respect to mooring systems based on design choices, substructure selected, mooring and dynamic power cable configuration, line makeup, environmental conditions, geographic location, and regulatory environment, as to make it impossible to review all permutations. So we have avoided doing this. A natural starting point for any nascent industry is to look to existing knowledge, and floating wind can certainly draw from the vast experience of offshore oil and gas. The paper explores this in more detail, but finds limited transferability. Oil and gas structures tend to be single, very large units operating in deep water and employing multiple mooring lines, whereas floating wind developments will typically be in shallow water, comprise large arrays of floating turbines, each with far fewer lines. Operating conditions may be much more dynamic, non-linear, and large turbine thrust forces need to be considered. Furthermore, whilst oil and gas is highly sensitive to operational safety conditions, it is much less so when it comes to cost. And that is in stark contrast to floating wind, where the imperative is to drive down LCOE. Next slide, please, Ilya. There's no global governing float standard. However, several international classification societies have developed standards, guidance, and recommended practice which incorporate existing rules. These will require harmonisation and further development in response to innovation and growing operational experience. Any design should comply with prescribed limit states as defined here. The ultimate limit state, or the ULS, which is the maximum structural stiffness or load carrying capacity of an intact system beyond which the probability of failure is unacceptable. The fatigue limit state, or the FLS, the maximum stress concentration or damage accumulation resulting in structural failure due to cyclic loading below the ULS. And the ALS, which is the accidental limit state, the minimum survival condition required to maintain structural integrity in a damaged condition for a specified return period. In addition to this, each design should consider robustness against possible systematic errors. For instance, the less mature technology, the higher the need for robustness. Redundancy considerations are an important part of mooring design and form part of the basis for selection of an appropriate consequence class. Redundancy is a commonly used term, but one which is often misunderstood. DNV in ST 119 defines redundancy as the ability of a component or system to maintain or restore its function after a failure of a member or connection has occurred. For example, if one mooring line is lost, the remaining part of the mooring system must meet the ALS criterion for at least a 1-year load, as well as a robustness check for the intact system within the specified return period. However, DNV goes on to provide guidance that in some cases, it's not so obvious if the station keeping system is redundant or not. For example, failure of a slack mooring line in a 3x1 line system causing a large drift off does not necessarily imply a system without redundancy. The provision of alternative load paths, or the N+1 concept, for example, the 3x2 line mooring spread shown here, is advocated as the preferred method of mitigating risk of single line failure, although redundancy may also be achieved via strengthening, i.e. improving the structural integrity, such as increasing the size of equipment used. So the practical application of redundancy is in fact the balance between the ULS and the ALS. Target safety levels may vary according to the regulatory environment, but to each design may be attributed a consequence class, and typically mooring systems are designed to achieve consequence class level 1, i.e. where failure is unlikely to lead to loss of life, collision with adjacent structures, or environmental impact, unless they are non-redundant, in which case consequence class 2 applies. Next slide, please, Ilya. Having determined there's limited transferability between oil and gas and floating offshore wind, there are still many lessons that can be learned. An earlier study into mooring failures in oil and gas floating production systems identified rates much higher than prescribed by the relevant design codes. Whilst this has no doubt improved in the past 10 years, DNV estimate failure rates for floating offshore wind of between 0.1 and 2%, and express an opinion that developers should plan for failure. Therefore, mooring integrity issues need to be given much greater consideration during the design phase and applied throughout the mooring lifecycle. Mooring integrity management is a process for ensuring moorings fitness for service over its entire lifecycle, managing the effects of damage, deterioration, changes in loading, and accidental overload. Mooring integrity management programs should detect abnormal conditions or factors outside the original design envelope through regular inspection and monitoring. The process is iterative, providing data that may be used to undertake remedial action, protect against accident or loss, estimate remaining life, or support life extension requests. The integrity management process provides an opportunity to adopt risk-based principles that consider the likelihood of damage and its potential consequences in order to develop a risk matrix. Mitigation should be put in place to reduce or remove the identified risks and/or the consequences of failure, and a list of initiation triggers should be developed to determine if parameters have changed. Immediate and short-term incident response planning should also be evaluated, along with the availability and condition of any spares or emergency repair equipment. The integrity management process should be defined as early as possible in the design phase and a risk-based inspection plan drawn up, identifying the frequency and scope of inspections, methods and equipment to be used. Direct measurement through continual monitoring, periodic measurement or visual inspections are preferred. However, inferences from indirect measurements, such as platform motions, may also be used, so-called digital twins. Next slide, please, Ilya. There are no reported failures in float mooring lines to date, but this is perhaps due to there being few small-scale demonstrator projects in the water. But if we are planning for failure by employing mooring integrity management programs, understanding the main threats and associated mitigations is critical. Importantly, we also need to understand what constitutes a failure. It does not necessarily imply a catastrophic event where damage causes the loss of one or more lines. For example, it may be a reduction in line tension in which the floater excursion falls outside the original design envelope, risking damage to the power cables, or indeed the preemptive replacement of equipment identified by an integrity management program as being damaged or degraded beyond design expectations. In each case, energy production may be interrupted, causing loss of revenue, if not a total loss of the floater. Again, we can learn from oil and gas experience. The aforementioned study identified the most prevalent causes of single-line failures as fatigue and corrosion, with 49% of damage sustained during operation, 90% of failures due to design issues, and 6% attributed to manufacturing. The most commonly failed component is chain, representing 46% of all events, of which almost half occurred in the upper sections, particularly the stopper fair lead. Behaviour of chain links in this section should therefore be carefully evaluated during the design phase to minimise the risk of failure, and particular attention should be paid to corrosion in the splash zone. However, chain is the most represented component, being present in 76% of surveyed systems and subject to the highest preemptive replacement, which suggests it can be adequately managed through a robust integrity programme. Similarly, steel wire rope accounted for 31% of all events and was also widely represented in 47% of systems. However, multiple line failure events are dominated by wire at 60% compared to 13% for chain. It's also worth noting that reported failures in polyester ropes, which represent only 3% of the total survey, were caused by mechanical damage. However, these statistics may be somewhat distorted as the use of polyester for permanent mooring lines was in its infancy at the time of the survey, with only 9% of facilities using or having used it. Consequently, prevalent failure modes may not yet have emerged. A small number of out-of-plane bending failures were also reported. These are becoming increasingly relevant, especially in systems with high pretensions, but are much less well understood. And one other less well understood but important factor is installation, which represents 18% of failures, with 22% of damage caused during the installation phase. A detailed risk assessment should be undertaken at the design stage. Detailed installation plans and handling procedures should be developed, and recording of the as-installed condition is critical to the future management of the system. So many of the underlying failure modes and degradation threats of oil and gas will be applicable to floating wind moorings, and the criticality of certain locations within the mooring line will remain important. However, it's anticipated that the use of chain and wire will significantly be reduced in favour of the synthetic rope and the employment of new technologies. So novel failure mechanisms will be particularly challenging and cannot be easily prevented by existing integrity management practices. Therefore, a level of conservatism is recommended alongside an enhanced inspection regime during the first 3 to 5 years of operation to capture infant mortality issues. The impact of regulatory shutting criteria in failed line conditions should also be understood. Allowable operating states and acceptable insurance risks should be identified, with mitigations and sparing strategies considered to improve overall availability. Next slide, please, Ilya. It's anticipated that innovation and the adoption of new technologies will address the various challenges and help drive down cost, as will industrialisation of production and deployment. We have introduced a number of key innovations and product extensions within the paper, including synthetic ropes, load reduction devices, digital twins, shared anchors and shared moorings, and tensioners and connectors for easy hookup and disconnection. However, a lack of experience or track record and its associated risks may preclude projects from securing adequate insurance cover. Furthermore, increased pressure to optimise mooring systems, the risk of serialisation of defects, and lack of readiness in the supply chain or local content availability could exacerbate this issue. Innovations will need to achieve sufficient technological readiness levels to secure project finance and insurance. But during the committee meetings, we identified several challenges to this process. Firstly, given very limited opportunities for the integration of new technology within demonstrator projects, how can projects quickly qualify to the highest TRL levels at commercial scale in order to meet the rapid LCOE reduction objectives? Secondly, it was considered that progress through TRL levels 1 to 5 is relatively straightforward. However, the question arose about who would be responsible for TRL assessment and accreditation, especially at the higher levels 6 and 7, and particularly when products perform as part of a system. And finally, we considered what the threshold would be at which insurers are comfortable underwriting new technologies, or must projects initially adopt the risk between leg 1 and leg 2. Furthermore, to attain the higher coverages, will insurers mandate independent evaluation schemes, for instance, type approval and classification that assess readiness and consider manufacturing elements? Suppliers should be ready to drive progress and provide transparency, and industry collaboration will be key to overcoming intellectual property issues and restrictive contractual clauses to allow an innovation's use across multiple projects. Technical risk assessment and mitigation strategies as part of an overall mooring integrity management programme will enable projects to properly handle the adoption of new technologies. Next slide, please, Ilya. The greatest opportunity for improvement is presented when things go wrong, and it's assumed the application of new designs, technologies and materials will result in unanticipated failures via new modes and novel mechanisms. Sharing details of these events will be hugely beneficial to our nascent industry and will help speed up the energy transition. However, commercial and intellectual property concerns present a significant barrier to achieving this. Procedural-based controls are required for handling information properly between designers, manufacturers, and operators, and transparency is therefore essential. But this is one area where oil and gas has been less successful. Failure rate data is not in the public domain, and since the 2014 study referenced earlier, information remains incomplete. Limited insurance cover is available for the floating wind sector, with reduced coverage, increased deductibles, and high premiums compared to bottom fixed wind, which is currently experiencing significant claims. Developers will need to demonstrate risk mitigation, but insurers may still decline or limit coverage. Finance could be difficult to secure on projects using unproven technologies or exhibiting limited track record. An early conservative approach is therefore advocated. However, the pressure to reduce LCOE through innovation and rapid transition to full-scale arrays is the paradox lying at the heart of the industry. To overcome this contradiction, the floating wind industry needs to take a radical approach, but a consensus between all stakeholders is required. Some mechanism is required to promote the sharing of all mooring integrity management data, not just failure events, and the early phases of any project will be of most interest. In this way, the industry could learn quickly together as anonymised results may be shared widely, insurers would be protected and in the long run, and all would benefit from lower premium levels. Otherwise, early failures in serialized, highly optimized and or non-redundant mooring systems may dramatically curtail future developments. Capability of the supply chain to meet mooring system component demand is another major challenge for the industry. The importance of working with experienced suppliers that have equipment or technology track record can pose a challenge to markets implementing local content targets. Building localized floating wind supply chains will require large investments and sustainable knowledge transfer mechanisms from established industry players. Finally, in summary, the initial work conducted by the Mooring Subcommittee has concluded the integrity management processes holistic, iterative characteristics can support the industry's path into technological maturity through rigorous monitoring of risks, associated implementation of mitigation measures at all project phases, and recommends an improved system for data sharing. Future detailed work, therefore, may likely focus on these challenges. Okay, I hope that gives you a good summary of the details within the white paper, and we look forward to receiving your questions. Thank you very much.
Okay, great. Thank you very much, David, for this very comprehensive overview of the mooring system white paper. Such great work, and I think it's a incredible work for the industry in general. So great, and right now we have approximately 35 minutes for the Q&A session, and it's a great opportunity for all of you to ask any questions you might have. We already received a few questions to begin the conversation, but please feel free to use the chat function on the right-hand side and just type it in, and I will read it to our panelists. So I guess we can begin with the more general questions, and the first one would be, any insights on the challenges and opportunities for shared anchoring or shared mooring systems in floating wind? And I guess we can start with Ralf, if you don't mind, then Jon, Aseem, and Alistair, and at the very end, if you have energy, David, you can say a few words.
Yes, if I may, I would like to hand over this question to someone of the others, because this is, I think it would be good to start with the technical aspect. Where are we coming from? Because insurance finally at the end would be a subject to discussion. So if I may, so someone else of the other three would be willing to answer.
Sounds good. Jon, are you feeling as answering this question?
Sure, I'll jump in, Ilya. The first one that strikes me is from that mooring integrity management point of view, is that you actually start putting connectors into multiple load paths, which is seen as a great challenge for actually managing the integrity. And that's what it can mean is you lead to a system with a failure mode in that connector that holds multiple mooring lines actually impacting multiple units. So you're actually bringing up your consequence side of the equation, which is something that needs consideration. The other one is that there is probably going to be a difference between shared anchors and shared mooring lines, and the understanding thereof of what impacts that is actually going to have on the system performance, especially if we start talking about the fatigue loading of some of those, I guess, midline connectors for joint mooring lines rather than just simply sharing anchors.
Okay, great. Thank you very much. Aseem?
Yeah, like this is a very interesting topic, and we are seeing a lot of interest in the industry on shared moorings, shared anchors to start with. And in addition to what Jon mentioned, I think another important aspect to consider is the wake interaction effects between the turbines, because that will affect the motions of the floaters, and which in turn will affect the moorings. Yeah, like it's an ongoing area of research to find out possible interaction effects, and like we did a research project with Glasgow University a few years back, but that was very high level, and a lot more needs to be done on this topic.
Great, thank you. Ali?
Yeah, I mean, I think just to echo the points. Sorry, coming through, okay?
Yes, all good.
Yeah, okay, yeah, sorry. Yeah, to echo the points, other presenters have made, it's within the Floating Offshore Wind Centre of Excellence, moorings focus group is certainly an area of a lot of interest, and a lot of people have been wanting to do further dives into this. I think one of the areas which hopefully lead on quite nicely to Ralph's contribution is there's not much public information about actual tests and loading that is out in the public domain, which is leading potentially insurers and insurability to be a bit apprehensive about how this can operate. And I think people still see it as quite a novel concept that needs a lot more research, but more than just a novel concept, we're now seeing it actually being used. And, obviously in the Equinor Highwind Tampin project, these are actually going to be implemented. So it's important that we work well as an industry to help perform adequate technology qualification of these components, and to make sure that the industry have a lot of knowledge that allows the insurers to have confidence when they're putting these shared anchor systems in the water.
Okay, great. Thank you very much.
Yeah, Ilya, my understanding is that there's been a lot more work done on shared anchors than shared mooring systems. And the obvious benefit is that you can potentially reduce the number of anchors being employed, and depending on the geometry, that could be up to a factor of 6. So it's significant. There's the opportunity. I guess the challenge is that these anchors will need to be able to resist multiple directional loading, and what effect that might have on the soil characteristics is also unknown. So yes, as Ali says, it warrants a lot further investigation.
Great.
Ilya, I'd also like to just make the point quickly that this is not the first time we've talked about shared moorings and shared anchors in the offshore industry. Aquaculture's been doing it for years, albeit there are different concerns and challenges in that industry. But I think it's important we don't just look to oil and gas as sort of the forefathers of mooring technology. There are other industries that are out there doing this, and I think there are lessons learned there that we can definitely, as I said, learn from and understand.
Great. I saw, Ralf, you raised your hand.
Yes, so this technical pre-discussion was very interesting, because I'm also coming from the engineering side. Originally, went into the insurance business. So from my understanding, I think insurers, it will be able to convince insurers about shared anchor systems once we are able as industry to show that it's like a serial production. Let me take this as an example. For example, we had one presentation, very interesting. I think, David, it was in the mooring subcommittee, where someone was presenting shared anchor piling principle, where we said that the advantage of, for example, piled anchors is that you can completely fix them and bring them onto the site in the summer season in year number 1, and then you can come back in year number 2 and fix everything else. So, which means, and this is not no anchor dragging process. It's a real controlled process. So not to say that anchor dragging would not be controlled, but you have this multi-direction approach. So I think we have more to dive into that and to make it more transparent. Also to follow Alistair's argument, to say that insurers then start, and also projects in the future start to understand why it is really possible also to participate at this enormous cost reduction potential, which is behind, of course.
I think it's also likely that the sort of shared anchor principle is more likely to be deployed in deep water environments. John, correct me if I'm wrong there. You know, it's more suitable to that, and a lot of the wind farms will possibly be in shallow environments, so it might not be entirely suitable.
Okay, great, thank you very much. And there's a question on top of that. What is the impact of shared moorings in the O&M stage? Any volunteers, if you would like to answer that question? Okay, I guess that's
I'll take a stab if you like, Ilya. We will have an opportunity to minimise costs, which is great because fundamentally there's going to be less components to inspect. However, we need to be also mindful of that. What we do inspect, we are actually going to be more careful. Once again, coming back to that consequence piece earlier. So I think overall, as far as OPEX goes, boat days goes, inspection techniques go, real positive. However, I think we will need to really consider what kind of techniques we are using, and do we actually need to jump into using, you know, some of the more novel techniques that are coming to ensure that we are comfortable with the state and the condition of those components.
Okay.
And there's a cost trade-off there. There's a cost trade-off there as well, John. But obviously, you'll have fewer anchors if you've got shared anchors. But you know, piling compared to drag embedment is much more expensive. So what's the trade-off there in terms of cost? You might have fewer anchors, but the relative cost may be higher for the installation.
Agreed, David. And that's where fundamentally coming up with your mooring design is not just coming up with your mooring design. We need to have that whole of field approach, understanding the floater technology, the turbine technology, impacts on efficiency if we're in the wake of other units because of our layout. So I guess moorings is not just one part of, it's not its own discipline. It needs to be considered within, I guess, the whole field and that real LCOE equation.
Great, thank you very much.
Just to add one point kind of generally on the, so I think there's maybe a bit of a lag on my side. But just to add another point on the shared anchor side as well is when we're looking at commercial scale floating wind, it's going to be important that we kind of admit that there will be failures in the future at some point. You know, when you have hundreds of floating wind turbines in the water, each one with three or more mooring lines, there's going to inevitably be a failure, no matter how good our design is. So how these shared anchors and shared mooring systems react under a failure scenario is going to be extremely important to understand, because that's, since there's such coupled systems, there's a lot more potential for knock-on effects following a failure.
Okay, Ali, thank you very much.
And also to add to that, I think even if you have to do a preemptive replacement of components, which would be required, it would be more challenging on a shared anchoring, and even more on a shared mooring system.
Okay, great. Thank you very much. Okay, so next question, as the person who is asking saying is most likely for Aseem, but others will please feel free to join to answer this question. And the question is there a push for a global regulatory framework as for the oil and gas led by class, which will lay down standards against which integrity management will be measured to mitigate risks, assure owners, operators, investors, and insurers? I guess we start with Aseem, and then others, please feel free to join.
Yeah, just can you repeat the question once? I think I have understood it, but just to be sure.
Yes,
Yeah.
sure. Is there a push for a global regulatory framework as for the oil and gas industry, led by CLAS, which will lay down standards against which integrity management will be measured to mitigate risks, assure owners, operators, investors, and insurers?
There is definitely an initiative within the company. I'm not sure if there's an industry-wide approach going on to come up with standards, but definitely DNV is working towards mooring integrity management standard for floating wind, basically floating renewables in general, and especially focusing on floating wind. So yes, to answer the question simply, yes, we are working towards that. We released our mooring integrity management standard for oil and gas last year, and now we are working basically include a specific standard for floating wind or floating renewables.
Okay, great. Thank you very much, Aseem. Great. Next question is, I guess, to all of you. Could you please enlighten us on the methods used to monitor the health of the mooring lines?
Yeah, I mean, there's a lot of existing methods that are used within oil and gas and aquaculture, like strain gauges and GPS monitoring as well. But I think what's going to be really important for commercial wind is ensuring that we're looking at efficient ways of monitoring global performance of assets so that you can quickly identify mooring failures or degradation in mooring. So, like mooring tension starting to reduce, or maybe creeping lines, for example. And so, with this, you're looking at kind of smarter systems that can monitor multiple assets at a time. So elements such as GPS monitoring are going to become quite useful because that can be done on a global scale and doesn't rely so much on individual components which could fail at some point in themselves.
Okay, great. Thank you very much, Ali. John?
I'll lead on to John, I guess now.
I'll pick up on Ali's points. There's a lot of technologies out there for monitoring, and things like strain gauging, load cells, inclinometers have been used in oil and gas to various levels of success, I guess I'll say. With, a fair bit of experience on a personal level on working with these systems. Unfortunately, they do have their issues for long-term mooring integrity and that long-term monitoring piece, which is where the importance of the digital twin comes up. And I guess it's really looking forward to technologies like SMIC, which is one of the ones which I'm very familiar with, on using not just the digital twin aspect of the DHBS, but also using all the other data you can collect in the field to actually come up with, have you got that mooring integrity? And there are smarter things we can be doing. It's not just offset monitoring, to be clear, with DHBS. It's also understanding, have you lost tension? Have you changed the characteristic performance of your system? So we can get a lot of insights from just global monitoring rather than those load cells, those strain gauges and so on, which have their own issues.
Okay, John, thank you very much.
And there will still be a need for direct inspection. So going out and physically looking at it, measuring it, assessing the condition of the mooring system. You've got to take all of this information in the round, and it should all be added into the model in order to improve all of the mooring integrity management practices.
Okay, great. Thank you. And I guess the next question will be first to Ralf. Is there such a thing as a general insured lifetime? And if it is, what is a general insured lifetime of mooring systems? So Ralf, if you have an answer to this question.
Yes, I needed some seconds to consider because this is a very interesting question. So from my own experience, I have now been working in the wind industry since '96, so 26 years and 15 years now in offshore wind, starting also with the small turbines in offshore wind. It was always the same that insurance coverage, full insurance coverage also against the breakdown as such will not be available for the full design lifetime. So this is fact. So the wind industry, for example, in bottom fix, they are providing, once the project has achieved full coverage, including damage due to defects, around 10 to 12 years from my experience, and sometimes also to 14 years full coverage, and then they are always reducing coverage to external perils, so to say. But this is accepted in the industry because the financing periods very often are parallel, so 12, 14, 16 years. So this is accepted by the projects. When it comes to mooring lines, this is more something where this is just from my experience, my recommendation would be to the projects more to say, not to look how long it is insurable, but from the beginning to decide for mooring line systems, which is very easily to repair, very easily to replace with a very low downtime. Downtime means very low loss of production, and not to rely on future insurance coverage, because this is a problem. Different to service contracts from the wind turbine suppliers, so the big O&M contracts, an insurance policy is cancelable every year. So you have to run to the insurers every year to renew your policies. So after 6, 7, 8 years, once your project had losses, it is not automatically given that you will receive insurance coverage. So just to consider. So major recommendation, which I also really wanted to give today, is from the design phase, definitely to do something which is later easily to be repaired, replaced with a low downtime. Most important feature.
Okay, great. Thank you very much. I think it's a very comprehensive overview. And yeah, I think the person is happy with the answer. Okay, next question is rather technical. Let's see if we can answer that one. Is there a difference on mooring system on the first floater that is connected to the grid than the floaters that are located further in the string? Any volunteers, since it's a technical question, and it's okay if we don't have a direct answer. Okay. Then we have a question.
Sorry, I was giving Ali a chance there just in case the lag got him. From my understanding, especially like if you are shooting the wake, you are going to have a slightly different loading. And in particular, when we get down to fatigue, which is likely to be the governing design limit state for offshore wind moorings, especially because we are operating at high main tensions with the high thrust loads. Once we see that wake effect kick in, we will see slightly different loading. And where that becomes a challenge is that if we are going to use common, or at least common components, if not common designs across a field, we will have different loading duties and therefore different predicted lives for some of the mooring components from the upwind system to the downwind system, which is going to be a consideration. I don't have any numbers to tell me to quantify what that difference is, but qualitatively, the units that are going to experience the highest thrust loads will probably see the largest fatigue consumption on their system. The other point I just wanted to raise is, especially if we go down to daisy-chained connectors for the power cables, we then talk about, well, which unit is actually more critical in the chain? Because if you lose just the unit at the end of that daisy chain is the idea of connecting multiple units together with the same power cable. If you lose the one at the end of the chain, so nothing else is connected to it, you only use production from one unit. But if you lose the unit which is towards the end, you might lose the production from 7 or 8 units. So then when it comes back to, and I guess I've said this a few times tonight, that criticality piece of what actually matters when you're looking at your mooring system integrity.
I see. Thank you very much, John. So Ali, any comment?
Yeah, it's an interesting point that as well. I guess it also very much depends on how you're going to go about your cable topology. So if you are, there's talk about some kind of bus bar type system where you have like static cables along the floor, then dynamic cables coming up to the floater, which makes it easier to remove one turbine without losing powers from the other. But that again then comes with its own issues. But I think, whilst I don't really have a definitive answer to the question, I'm afraid these are the kind of questions that would be answered when you're looking at kind of pre-commercial farms. But what we're trying to do in floating wind is almost miss that step out. We're going from what is a kind of a concept where you've got demonstrators in the water, you know, with 5 or 6 units, and we're looking to accelerate that all the way up to gigawatt scale floating wind. And so we'll be missing out a lot of those lessons learned, which might answer questions like that along the way. So whilst, you know, I don't have an answer to that question, this shows these are the types of questions that need answered, and this is where academia, research organizations can help try and find these questions and try and answer them to allow for that rollout of gigawatt scale floating wind.
Okay, great. Thank you very much for answering this technical question. So the next question, I guess, David, is for you. If you have ideas, and this person asked a few questions, so I'll try to phrase them so it's easy to understand. So the question is, are there any distinctions made in design philosophy between harsh environment, hurricanes, typhoons, and some other natural hazards environments? I guess that's the second question, are TRL levels environment specific? And there's a more technical question, what are the typical ALS return periods used for floating wind farms? So if you have information, that would be great.
Yeah, okay, so each one of those in turn. The first one, yes, of course, the design parameters are going to be different for each wind farm based on the location, the environmental conditions. So yeah, there are going to be lots of different design decisions, and of course, that just doesn't relate to the mooring, but that relates to the floater type. So yeah, I mean, you could have many different iterations of designs for the same environment. It depends on the developer decisions, I guess. The second part of the question related to TRL levels, is that correct?
Mm-hmm. Yes.
Yeah, okay, so TRLs, yeah, of course, you've got lots of different environments that are challenging. So an environment with high seismic activity is going to be very different challenge to an area with typhoon activity. So a product that has a TRL level in one environment doesn't necessarily have the same TRL level in another environment, and they should be assessed on a case-by-case basis. I think that's probably the simplest answer to that question. And the third point was, Ilya, remind me?
Yes, sure. So I think ALS return periods used for floating wind farms.
Yeah, the specified in DMV stand is a 500-year return period at the moment in ST 119. Aseem, that's correct, isn't it?
Yeah, that's the robustness check where like the system is intact, but you check it for 500-year return. And then for the redundancy check, you have 1-year return requirement, 1-year return environmental period. Yeah.
Yes.
Okay, great. David, thank you very much for answering such technical questions. That's great. So I hope the audience learned from that. The next question, I think more to Ralf. What would you expect the requirements to be for a mooring system to be considered proven by insurers? And prior to that proven status being achieved, would you expect to insurers to provide leg 1 cover only?
So we did this experiment already with 3 or 4 floating offshore wind farms in Europe. So we have experience, we have answers already, and the reason is that why I have to a little more explain is that you have to understand the insurance business more. So for one floating wind farm in the future, you will need at least 10 insurance companies. Yeah, so at least for one wind farm, and so, which means that you have not to talk to one and they have an opinion about something. You have really to talk to the industry as such, to the insurance industry, which means for mooring lines, This was one of my jobs at one of the further recent projects, which also received non-recourse project finance, was exactly to give a recommendation with respect to the mooring lines. I do not go more into detail, but really what we did is, for this instance, we really tried not to use components without any track record. So this was a major message. Because for the public here, leg 1 is the coverage which excludes the full consequential damage and the full loss of revenue. Complete exclusion if even the smallest checker has a defect and then a damage to the floater occurs. So there's no money and no coverage at all. So which is very difficult and have never been done in bottom fix. So bottom fix was never starting with leg 1. So we should really try to avoid everything to start with leg 1 coverage, which means that we at the moment we are discussing with the technicians and insurance companies, and in the business as such we are discussing this, how we can convince insurers to provide coverage for leg 2, which would then less limited coverage for the defects consequence for mooring lines. So this is an internal process at the moment. This is exactly why we are having these subcommittees at the WFO. So every member at the moment knows what we are always discussing. So this is the real message, and or Catapult also what they are doing a very great job with this, exactly to define these thresholds. At the moment they are not defined insurance-wise. So we have some ideas, because to be more concrete, 15 years ago, when we started with the warranty insurance for wind turbines offshore, this was also done by myself in my former position at an insurance broker. We managed to convince insurance companies that after 8,000 successful operational hours, automatically in the policies, coverage switched from leg 1 to leg 2. Yeah, so which means this was, and it's always good if you have to convince such a lot of insurance companies not always to remain with these risk engineering discussions, because they will never end, and you have to do this for every project. You need something on which you can rely, and I think at the moment I think we can discuss in the future to reduce perhaps these operational hours for mooring line systems or something. But to start with, I would think it would be very reasonable and a good point if, as a very first starting point, we at least could say that after some thousand successful operational hours, it is crystal clear that insurers agree to increase the coverage level. So to start with, this is a really crucial starting point, and because you need this, because until we do not have this in floating offshore wind, it will be very problematic for finance, because finance has always to consider these effects with reserve accounts and contingencies, and you cannot make a finance plan without having these threshold information.
Okay, Ralf, thank you very much for this comprehensive answer. Our next question is for Aseem. What are the main trends at DNV are seeing with respect to floating offshore wind mooring systems, and the key challenges, opportunities from a class agency perspective?
Yeah, in terms of key trends, like we expect in short term, the mooring systems will use traditional materials like chain wire, polyester, along with accessories such as clump face, buoyancy elements as required. But in long term, new materials and new components like nylon of load reduction devices will be qualified, and which will make mooring systems more optimized and simpler. Another trend we are seeing is, like, as the turbine capacities are going up to 15 megawatts and beyond, the number of mooring lines will increase to keep the size of the mooring lines, chain sizes within, not becoming too big. So we will be moving from typically presently most of the systems being proposed like or installed a 3 mooring line system, but we are moving towards more like 4 to 6 mooring line systems. In terms of challenges, what we see is it's the because of the number of units involved and the large lengths of mooring lines required, operation and maintenance and installation is going to be a challenging aspect, and which should be considered and optimized in the design. There will be a lot of capex and opex pressure on the industry to innovate in these aspects. So there will be a lot of, like as I just mentioned, there would be new components which will be proposed and which will need to be qualified. In terms of installation methods and operation O&M methodologies, there would be a need to come up with methodologies which are not cutting like corners, but at the same time are cost effective. So that is going to be, in our opinion, one of the major challenges.
Thank you very much. Next question is to Jon. It would be great to hear your comment on regulatory shut-in criteria and sparring strategies based on AMOG's earlier oil and gas study. What can floating offshore wind learn from this to improve overall availability and mitigate risk?
Yeah, thanks, Ilya. I think the point of regulatory shut-in needs to be acknowledged. You can design a system that meets all your technical requirements and may even meet class requirements, but the regulator is not allowing you to operate in a single line damage condition, which is what we've found in some oil and gas experience when we've got multiple lines in a single cluster. We're talking 7 or 6 or 8 mooring lines in a single cluster. Some regulators, so the offshore regulator, the safety regulator in certain countries, are saying, no, with one line failed, this is not a safe condition, even though it may have been demonstrated to that. So it's very key when you start making those decisions on redundancy that there's engagement with both the regulator and class and also insurance to understand what the insurable risk is, as well as what is your corporate risk, as well as what the regulator will let you get away with. On the sparing is a really interesting point, because the lead times for mooring components are only going to go up, especially as floating wind takes off. And what it means is that if a mooring leg fails in system, it's not just 12 months, because you might not even have the first slot with the fabricator and the manufacturer. You might be waiting 3 or 4 years, and thus you're losing that unit, and then you're probably making real decisions about not even reinstating it. So what we found is that sparing philosophy was a real key decision point to make sure you keep high availability of the oil and gas system. But straight away, when we saw those kind of statistics, and we're talking about going to many, many more mooring lines in the future for offshore wind, that sparing piece is really crucial. But we also need to balance that out with CapEx and making sure we don't drive LCOE too high. So it's going to be one of these hard decisions, and it's probably worth actually doing the studies to understand where it goes.
Sounds good. Thank you very much.
Just an additional point there, Ilya. I mean, it's a really good opportunity for the industry, because the whole serialization piece, if you've got a number of wind farms employing similar mooring systems, it might be that the sparing strategy or those spares can actually be shared across a number of wind farms. It doesn't have to be one wind farm. So there's a great opportunity there for the industry to harmonise and to be able to share spares. And as I said, the opportunity is there because we have a serialization approach. You know, you can have one spare that's going to cover the whole wind farm, whereas oil and gas, every mooring tends to be different. So the spares would only suit the one project. So again, there's a great opportunity there for floating wind to be smarter with its sparing strategies.
Okay, great. We actually do have interesting questions to Ali and to Ralf, but because of the time, and we have to respect your time and of the audience, we have to finish this webinar. That was a special webinar. We're probably going to have some more in the future. And as for now, I would just say, please join us after the summer break for our next regular webinar this time. That's going to be on offshore wind market updates. And as for now, thanks very much, David, Alistair, Ralf, Jon, and Aseem for your time today. Thank you very much for sharing your technical expertise on the topic. That was a great discussion, I believe. It's going to be posted on our YouTube channel, and I hope to work together with you on further events. Enjoy the rest of the day, and bye-bye.
Thank you.
Thank you.
Thanks very much.